This is a hydrogen atom which supposedly makes up over 70% of the universe. It's an artist's conception, which is supposed to illustrate the all-mysterious wave function, a mathematical construct, which isn't real because the wave is just a probability density function. The areas that are more densely orange represent areas where the electron is more likely to be detected or collapsed. The Copenhagen interpretation of quantum mechanics states that systems at the quantum level do not have definite properties prior to being observed interacted with, and that it is observation which collapses an otherwise indefinite state of the universe into one which abides by classical mechanics. Quantum mechanics, therefore, cannot deduce definite properties of quantum scale matter, rather, it uses probability distributions, known as wave functions, to deduce the probability of various classical states upon observation. The consequences of not having definite properties means that we couldn't capture a more detailed photo of this atom, even if we had a camera that possessed an infinitude of pixel space. Now, where else do we happen to see phenomena that is similar to this? The answer is video games. In video games, to conserve computer memory and improve rendering speed, game designers use something called procedural generation to create textures and details of the world. As the player approaches objects in the simulated world, the objects are rendered in detail proportionate to the vantage point of the player. If the player is near a tree, for example, they can view the tree bark and leaves in exquisite detail. However, the game will not have generated the bark and leaves of every tree in the simulation, because the player is not currently observing those features of the simulation, and rendering all such features across the entire world would be a tremendous waste of computing power. So after procedural generation, the image above may look like this instead. This shows that real reality and virtual reality can share similar conceptual designs, and we can prove all of this simply by observing the hydrogen atom. Is it proof that we are living in a simulation? Believe it or not, some very reputable quantum computer scientists believe this, including Seth Lloyd, the originator of the first technologically feasible design for a working quantum computer, who even wrote this book about it. For the curious at heart, here is some useful material for understanding what the wave function is and is not. The above video describes the phenomena observed during the double-slit experiment. Specifically, how a beam of electrons going through two slits/holes in a wall don't create just two rows of impact on the subsequent screen thereafter directly in front on the holes, but rather a series of vertical rows of impact with empty spaces of no impact spots in between, just as you add C if you assumed the electron's location was a wave, which would superimpose on itself via constructive interference. The wave equation, or matter waves, is a mathematical construct. It was first hypothesized in 1924 by Louise de Broglie, Matter Wave Wikipedia. What's waving, or rather changing, is the probability that an object will be measured in this state or that state. The state could be location, energy, momentum, etc. At any given time, the precise state of a particle is not known, and so must be assigned a probability distribution which describes a range. However, this distribution evolves with time, and the way it evolves can be mathematically described using a wave function. We use similar wave functions, a sinusoidal wave for instance, to describe the rise and fall of the market value of houses, which periodically go up and down in a predictable periodized fashion throughout the year. However, the wave in this case is purely just a mathematical construct. One major consequence with matter waves is that they seem to violate the principle of locality. See quantum non-locality Wikipedia. There is no denying that matter waves absolutely violate our intuition of what philosophers have called local realism. For example, the matter waves described above can superimpose on each other, or cancel each other out just like real waves do. This phenomena completely destroys any intuitive notion that reality has definite properties, or can be continuously broken down into smaller and smaller pieces of well-defined bits.